Okay, so this is the start of chapter 2. So as far as what chapter 2 of this course is concerned, there are several learning objectives for this chapter. One is just to introduce the concept of energy and to define its various forms. We're also going to discuss the nature of internal energy, and we're going to describe the concept of heat and the terminology associated with energy transfer by heat. Other objectives include define the concept of work, including electrical work and several forms of mechanical work. We're going to introduce the first law of thermodynamics, which includes energy balances and mechanisms of energy transfer. And then we're going to determine that a fluid flow across a control surface of a control volume carries energy across the control surface. So we're going to look at energy being carried by a fluid, and as well as an introduction to energy efficiencies. So what I'd like to start off by is looking at an example. We've learned that energy cannot be created or destroyed. We talked about that in a prior chapter. But how do we use this to understand real systems, right? So let's look at this example. Let's say that I have a room, and that room is perfectly insulated, right? So no heat can travel in or out of the room. And in that room, I have a refrigerator where the refrigerator of the door is open, right? And the refrigerator is plugged into an electrical socket where electricity is supplied to the room from the outside. So the question is, what will happen to the temperature of the air in the room over time? So the three options is, will the temperature increase, will it decrease, or will the temperature remain the same? So again, if you think about what's happening, right, I have cold air inside the refrigerator, but the door's open, and then the refrigerator rejects the hot air through the back. But all that's happening inside the room. And so when I normally ask this question to my brick and mortar class, the class when I teach it in the classroom to other students, the response is, there's different people that respond different ways, but according to the law of thermodynamics, what would happen is the temperature of the room would increase. And the reason is because the only energy that's crossing the boundary is electrical work crossing through the wall into the electric socket. There's no energy leaving the system because all energy transfer is recognized at the boundary. So if the first law of thermodynamics, which again, I think I wrote it out in the prior chapter, sort of introduced it. If I look at the first law of thermodynamics, what it tells me is that all energy entering into a system minus all energy leaving the system has to equal the change of energy of the system. So in this case, what's happening is that all I have is an energy in. I have no energy leaving the system. So all the energy in the system has to result in an increase in energy of the system. And that results in an increase in air temperature. And that's independent of the efficiency of the refrigerator. So as we go through this, we're going to be looking at ways to understand the first law, where that example we looked at is just one example of how we can do that. So let's first look at how to define what total energy is, right? Total energy of a system. The total energy is the sum of all forms of energy. So that includes thermal, mechanical, kinetic, potential, electric, magnetic, chemical, and nuclear. Now, we're not going to be covering all these different forms, but we are going to basically be looking at quantifying how much energy a system possesses. So it's common practice to designate the energy possessed by a system with the notation of E that represents the sum total of all the forms of energy. And then little e represents that in terms of specific energy. Remember, when we talk about the word specific energy means per mass. Okay, so that is designated usually by a lowercase letter. But what's even more what we're going to be really looking for in thermodynamics is this term, the change in energy of a system, right? The change in energy of the system is resultant by a process that occurred. So a process occurred on the system, causing that system to have an energy change. So that is represented by delta E. So again, different forms of energy. Macroscopic would be defined as those forms of energy that a system possesses as a whole with respect to some outside reference frame. Right? Microscopic would be those forms of energy related to the molecular structure of a system and a degree of molecular activity. These are independent of the outside frame. So when we look at internal energy, right? Internal energy is the sum of all forms of microscopic energy. It's designated by U. Let me go ahead and erase that extra line that appeared. It's designated by U. U is represented by internal energy. So that can be, for example, if a process happens and the temperature of the system increased, for example, that would be in a form of internal energy because molecular activity increased. Or if I add more mass to a system, that mass, for example, could increase the internal energy of the system. Other forms of energy, for example, is kinetic, right? The energy a system possesses as a result of its motion relative to a reference frame. So that would be a macroscopic form, right? So if I have a system, for example, a car, if my car is a system, the car is moving at a velocity, and I compare that to a stationary object, that car has a kinetic energy relative to the velocity. Now, again, kinetic energy can be put into specific terms. If I divide through by mass, my total kinetic energy would just be v squared over 2 as opposed to mv squared over 2. Next is potential energy. The energy of a system possesses as a result of its elevation, right? So if I have an object or system that's, for example, a box, and my box is at a 10 meters high, that mgh or mgz would be the potential energy, right? If I divide through by mass, I get it in terms of specific energy. So the total energy of a system, the total energy, right, E, that total energy would be a sum total of the internal energy plus the kinetic energy plus the potential energy of a system. So U plus mv squared over 2 plus mgz. Now, if I put that in terms of specific energy, right, divide through by mass, I have little u, little ke, little pe. So again, that would be the total energy that a system possesses. And we're going to be looking at that. So the total energy that a system possesses, or the change in total energy that a system possesses, is going to be a result of some process. So let's look at a stationary system, right? So if I'm looking at a stationary system or closed systems whose velocity and elevation remain constant during a process. So that means that the kinetic and potential energies of the system never change, right? So if I have a car that's driving on a plateau and that plateau has a certain altitude and the car has a certain velocity, and I look at the change in the energy of the car over a certain amount of time, if the velocity is the same and the height is the same, there's no change in kinetic and potential energy. So the notation would be the change in energy of a system is equal to the change in internal energy plus the change in kinetic energy plus the change in potential energy. So if my system is stationary, right, it's not moving, or if I have a system that's moving and it's not changing height or speed, my kinetic and potential energy changes are 0, which result in the fact that the total energy of the system has to be equal to the change in internal energy. And that's what's great about the first law is that we make certain assumptions. So this delta E is part of the whole energy balance, right? We looked earlier, and I'm going to define the E in and E outs later, but if I have a system, if I have a potato, right, the energy into the potato minus the energy out of the potato equals the change in energy of the potato. If my potato is stationary and not moving, that means that the sum total of the change in energy has to be sum total of the internal energy plus kinetic change plus potential change. If my potato doesn't move, well, the change in potential and kinetic energy of the potato is 0. So that means any change in energy, period, of the potato has to be equal to the change in internal energy, because that's what the first law is telling me. So that's what it does. The first law allows you to look at energy interactions based on certain assumptions. You can cross out the ones that don't belong, and what you're left with is the only form of energy that interacts with a system, right? So what about for flowing fluids? The energy of a flowing fluid is often expressed in terms of energy flow rate or energy per time. So that's usually, excuse me, I'm not sure why I keep getting these dashed lines or these long lines appearing. My energy of a flowing fluid, or any sort of flowing energy, which is usually designated by a dot, has to equal my mass flow rate times the energy of the flowing fluid, right? And then that is going to be equal to basically watts. If you look at it, I have flowing mass flow rate, right? I have kilograms per second for mass flow rate. Well, lowercase e here, right? That's specific energy. So the mass flow rate times the specific energy. If I do the dimensional analysis, this gives me kilojoules per second or kilowatts, right? Watts is energy in motion, joules per second. Well, kilowatts is kilojoules per second. Again, we have to understand that m dot is the mass flow rate of the fluid. It's the mass per unit time flowing. All right. So now let's look at the terms of energy transfer, right? Energy transfer, again, if I go back to my first law, energy transfer would be these terms, E in and E out, the energy into a system and the energy leaving a system. So energy can cross the boundary of a closed system in only two forms, heat and work. That is it, right? Closed system. Remember, a closed system, by definition, a closed system means the mass is constant. So no mass crossing the boundary. That's for a closed system. An open system has mass crossing the boundary. A closed system has no mass crossing the boundary. So energy transfer through a closed system only occurs by heat and work. So let's look first at heat. What is heat? Heat is the form of energy that is transferred between two systems by virtue of a temperature difference, right? Or basically a system and its surroundings. So let's look at this. Let's say that we take a can of soda. Let's start here. Let's say we take a can of soda out of the refrigerator, right? I'm from an area of the country where we say soda, not pop. So I'm going to call it soda. So let's say we take a can of soda out of the refrigerator. It's at 5 degrees Celsius. And the surroundings, let's say the room air is at 25 degrees Celsius. It's obvious that heat is going to travel from the room into the can of soda at a certain heat rate, right? What does that mean, heat rate? That means that the amount of heat traveling, the amount of energy traveling per second. So let's say it's 16 joules of energy, of heat transfer per second is occurring to the soda. So what happens as the soda increases in temperature? Let's say after a time, the soda can is the temperature of the soda is at 15 degrees Celsius, right? So that means I have a decrease in heat transfer. My heat transfer rate is not quite as fast. Maybe at that point it's 8 joules per second because the temperature difference is less. What's going to happen is that it's going to keep the room is going to keep the temperature difference between the cold soda can and the warm air is going to make it so that heat transfer is going to take place until the can reaches the temperature of the ambient air, at which point no heat transfer occurs. So another point to make is that an energy interaction is heat only if it takes place because of a temperature difference. No heat transfer can take place between two bodies at the same temperature. So here's the other example. Let's say I have a baked potato. The baked potato is hot. The surrounding air is cool relative to the baked potato. I take my boundary of the baked potato to be the skin around the baked potato, and heat is traveling, right? Energy is traveling, sorry, from inside the potato through the boundary out to the outside in the form of heat. A system doesn't possess heat. A system possesses energy and gives off or receives energy in the form of heat that converts it into internal energy of the system, or basically it just changes form. Heat is energy in motion. Heat is energy in transition. So you can't say I possess a lot of heat because I'm hot. You would say my temperature of my body is high. Therefore, my body is giving off energy to the environment in the form of heat because heat is only recognized as energy transfer from one point to another. And it's only recognized at the boundary of a system. Energy is recognized only as it crosses the boundary of a system, right? So I can't say a system possesses heat or a system has heat. I would say this that heat is traveling either from or to the system across the boundary because heat transfer is only, always, under all circumstances, only recognized at the boundary as it crosses the boundary. Okay, let's look at some notation. Heat is a form of energy transfer and thus has energy units. The amount of heat transferred between two systems during a process that moves from one state to another is denoted as Q12 or Q, right? Let's say I move that I have heat transfer occurring that causes a system to change from state 1 to state 2, right? Let's say I have a cup of hot coffee. The hot coffee is at 90 degrees Celsius, and after a time now, the coffee is at 70 degrees Celsius. State 1, I'm at 90 degrees Celsius. State 2, I'm at 70 degrees Celsius. The heat transfer that occurred to cause a temperature change will be designated as Q12. I can also look at heat transfer per unit mass. So if I take the amount of heat transfer divided by the mass, then I end up having what I call heat transfer per mass. It is not called specific heat. Specific heat is something else that we're going to cover later. Heat transfer per unit mass. Heat transfer rate is denoted as Q dot, right? So if I want to know the amount of heat transferred during a process, I say the amount of heat that was transferred in kilojoules equals the integral of the amount of heat transfer in watts integrated over that time period, right? This would be kilojoules. This would be kilowatts or kilojoules per second. If I integrate over the time span that the process occurred, I will get the total amount of heat that was transferred in kilojoules based on the rate of heat in kilowatts. Okay, I want to bring to your attention something else here. Now, we're talking about heat transfer. What happens if I have a process that is that occurs of which no heat transfer takes place? That process has a special name to it. It is called an adiabatic process. Again, an adiabatic process is a process in which no heat transfer takes place. So then the questions I get is, how is a process adiabatic? Well, let's look at two cases here. If a system is well insulated, so that only a negligible amount of heat can pass through the boundary, the system is adiabatic, right? So let's say I have a system here. Here's the boundary, and it is insulated. No heat can cross the boundary because it is insulated, therefore it is adiabatic. Another way to look at it is if I have a system, and let's say this inside the system is 25 degrees. Here's the boundary, right? And then the outside of the system and the surroundings at 25 degrees also. No heat transfer occurs because there's no temperature difference. So then the question I get sometimes is, well, if the temperature of the system is changing, therefore heat transfer has to happen. That is not true. I can have a system where I have work crossing a boundary, right? We had the example earlier of the refrigerator. The refrigerator had no heat transfer occurring across the boundary. It was electric work crossing the boundary going to the refrigerator. But yet the temperature of the room increased due to the fact that the refrigerator was in a perfectly insulated room and the doors were open. That is the case of a temperature increase, but the process was adiabatic, right? The process of the refrigerator using electricity. That process made the air inside of the room go up. So temperature increase occurred, but yet no heat transfer occurred. Why? Well, that's because the electric work crossing the boundary was converted into thermal energy inside the system. But since I only recognize heat transfer at the boundary, no heat transfer took place because everything happened inside the system. I only recognize the fact that work crossed the boundary. Right? And so, but there's also cases where heat transfer can take place and there's no temperature change. What do I mean? Well, if I have a pot of water that's boiling, right, on a burner, right, my water is boiling. So what temperature is the water at? The temperature is at 100 degrees Celsius because at 1 atmosphere, water boils at 100 degrees Celsius. Heat is being transferred across the boundary, which is defined as the saucepan, right? So I have heat rate occurring where heat is going into the system, but yet temperature change is not happening because all of the energy is going into converting the liquid water into steam. So that is not an adiabatic process, but yet the temperature is constant. So you have to be careful. Isothermal, which means constant temperature, is not always the same as adiabatic, which means no heat transfer.